In this video, I'm going to explain what the Con operator on Hochschild homology is. The Con operator is the self-map of Hochschild homology of degree 1, and the slogan is that the Con operator corresponds to the de Rham differential under the HKR theorem. That is what you should keep in mind and what we will make precise today. Also, I wanted to recall that if you're watching these videos, and hopefully some of you will regularly watch these videos, we'll upload roughly 2 videos a week. Then also if you have questions or want to join discussions, come either to our forum or to the exercises/discussion/coffee sessions that we held on Thursdays. Hi, I'm Thomas Nikolaus from Mathematics Münster. So the Con operator is an operator on Hochschild homology. So let's remember that Hochschild homology was defined in the following setting. K is a commutative ground ring, and R was a K algebra, or is a K algebra. And then Hochschild homology, the Hochschild homology groups, H star, are relative K, were the homology groups of the Hochschild chain complex. And the Hochschild chain complex was denoted RHH, R relative K. And we have that the Hochschild chain complex, R relative K, that is given by the chain complex which took the form R, and then we had a differential partial, R tensor R, and here we had 3 copies of R and so on. And this is an object in the derived category of K, in other words, a chain complex over K. Okay, so that's a Hochschild complex. And I mean, of course, there's a little bit of a fine print here, which I'm keeping under the rug for a moment, namely that if R is not flat over K, then we want to resolve by DGA. And then we consider all these guys as DGAs. So I'll indicate that by putting a little L over here. So then in fact this whole thing will become a double complex, and then we took the total complex of that double complex. But in fact, actually I think it's a little easier to ignore that and consider that a technicality. Okay, and the main result in some sense, the actually defining result in a way historically, is the HKR theorem. HKR theorem. And what is the statement? The statement is that if R over K has flat cotangent complex, so R relative K flat in dimension 0. And recall, we didn't talk about the cotangent complex, but we will have a separate lecture about the cotangent complex. So if you don't know the cotangent complex at this point, you can just think of R being a polynomial ring, or more generally a smooth or insmooth algebra. And the statement is that then the Hochschild homology is isomorphic to the de Rham complex. Okay. And here one has to be a little bit careful as to what this actually means. I mean, the first thing, which unfortunately I didn't write, note that for this to make sense, you have to require R to be commutative. Otherwise, the cotangent complex isn't even defined. Well, I guess there is an E1 cotangent complex, but we want to take the simplicial commutative for animated cotangent complex, the algebraic classical cotangent complex here. And then if R is actually commutative over K, then this is a graded commutative ring. Right? The Hochschild complex is a CDGA, and then the Hochschild homology groups are a graded commutative ring. And so is the right-hand side. The de Rham complex is just the exterior algebra of the Kähler differentials. So it's also a graded commutative ring, and this is an isomorphism of graded commutative rings. There is potential for confusion here though, because the right-hand side, of course, is called the de Rham complex, and it has a de Rham differential. Right? There is a de Rham differential D from omega star R relative K into omega star plus 1 R relative K. The usual de Rham differential, which is defined, I guess it's just defined in degree 0, this is R, and in degree 1 it's omega 1. So there it is, just the thing which comes by definition. The D operator comes by definition of the Kähler differentials, and then you extend it to satisfy the graded Leibniz rule. And that uniquely determines it. So the thing is, the right-hand side is a chain complex. But this isomorphism has nothing to do with this differential D. In fact, it's a little bit funny, and this is why very often it's very easy to confuse the statement of the HKR theorem if one just says the Hochschild homology is the de Rham complex. Because then, I mean, what would that mean? How are the homology groups are not a chain complex, right? If at best, then the Hochschild homology is itself a chain complex, maybe this chain complex. But here you see this has homological, the differential here has homological degree minus 1. It decreases the degree, whereas the de Rham differential increases the degree. So this can't even match, it doesn't even parse the statement that this would be equivalent, and in fact it's not the statement. Okay, but, and this is the content of what I will do now, there is some structure on the Hochschild homology groups which resembles the de Rham differential on this side. And this is what the con operator is. So let me define that structure for you. So R in associative K algebra then we define a K-linear map B from the Hochschild homology in degree of R relative K in degree n. And this is not the Hochschild homology group, but it's the nth guy of the Hochschild chain complex. Right? And it goes to Hochschild R relative K n plus 1. And what is the formula? As follows, we just send, B of R0 tensor ... Rn, an elementary tensor. This gets mapped to the following sum. It's the sum over all sigma in Cn plus 1. What is Cn plus 1? Cn plus 1 is the cyclic group with n plus 1 elements, but we want to think of it as permutations, the group of cyclic permutations of the set 0 through n. Okay, and now we want to do minus 1 to the n sigma of 0. And now we have 1 tensor R sigma minus 1 to the n R sigma tensor 1. And what is R sigma? R sigma is just defined to be you permute the factors R0 through Rn according to sigma. So in other words, R sigma 0 tensor ... tensor R sigma n. Okay, that is the definition of the con operator B. And this formula looks a little bit complicated. We'll study it a little bit in a second. But for the moment, let me just say there is a more systematic way of arriving at this equation. And this has to do with what is called cyclic objects, which were introduced by Kohn when he introduced this operator. We're not going to do that now. In fact, actually, we're later going to even generalize this more to the topological setting and then give you a very systematic way of thinking about this operator. For the moment, we just take this formula as its definition. And at this point, there's properties of the operator B which can be checked, and that is an exercise which I want to recommend you do at this point, or at least I sort of do parts of it because it's going to be a little bit lengthy and possibly a little bit annoying to do it all the way, but the exercise is to check that this operator B satisfies the equation that B squared equals 0 and dB plus BD equals 0. Okay, now I'll give you a couple seconds while I wipe the board. Okay, so I hope you could familiarize yourself with the definition a little bit by going through this exercise, or at least look at it. And one consequence of that exercise is, or like a restatement of what the statement of the exercise is that the operator B equips the Hochschild complex HHR relative K with the structure of a differential graded module over the DG algebra DGA, which we call A, and which is just defined to be ZB mod B squared, where B has degree 1. So we're going to reuse homological degree throughout. So B has degree 1, and I mean differential is 0. Right? This is a DGA by declaring the differential just to be 0. And then this guy has a differential given by the Hochschild differential, which we also wrote partial. And then the statement is that this is a module over this guy. And note, I mean, one has to be a little bit careful with the equation dB plus dBd. This depends a little bit on how you exactly distribute signs in the tensor product. Okay, so that's a DGA. And another way of writing this DGA is, in fact, it's a homology. So this is, in fact, I mean, you know, it's a DGA. We consider it as a DGA with this differential, but of course it's just a graded algebra. We never actually, I mean, the differential 0, it means just it's a graded algebra, and as such it's actually the homology of the circle with values in Z. And maybe actually this circle T is the group U1, the circle group. Because the circle group is a group, it's an abelian group, it turns out that the homology, the group homology of that guy, or like the homology of the classifying space, will inherit, let me say that again. It's a group. So the homology of the space inherits a product called the Pontryagin product, and as such, it's the exterior algebra on a generator in degree 1. Sorry, it doesn't matter that it's abelian or not for this statement. We just use the Pontryagin product. Okay, so it's actually a module over that. And what is this bias? I mean, this, for example, immediately implies if I have a DG module, then the homology will be a module over the homology of that A. So in other words, the homology of our chain complex is actually a graded module over ZB mod B squared. In particular, there is an operator B, which goes from the Hochschild homology R relative K into the Hochschild homology star plus 1 R relative K. And this also has the property that B squared equals 0. Right, it's just, I mean, you don't need to talk about DG modules or stuff. This just follows from the fact that we have the equation dB plus BD. This implies immediately that the B operator descends to an operator on homology. Right, it sends cycles to cycles and boundaries to boundaries. So it gives you this operator on homology, and we will notationally not distinguish between the operator B and its effect on homology. Okay, at this point, the careful watcher of this video, I was going to say the reader, but I guess you're watching here. So the person who is very careful might object that actually now I'm cheating a little bit here. What I did, in fact, was I defined the con operator just for an associative algebra, taking the usual Hochschild complex. But of course, in fact, remember, we had to do this little derivation in DGA business. So I did that in order to simplify the discussion, but the claim is that everything I said so far just goes through for DGAs. So at this point, it would be good if you try to understand what's going on, to just go back to the definition of B and just try to think how you define B if the ring actually was a DGA. And in fact, it's exactly straightforward. Just in the double complex, you use the exact same formula. And then the claim is everything I said so far goes through also in the DGA case. There's one fact which I want to use now about Hochschild homology. And this fact is if R is commutative, then the con operator B, see the con operator here is then a self-map of Hochschild homology, and we saw by means of the shuffle product that Hochschild homology has a product structure. And the claim is that it's compatible with the structure, and what would that mean? That means that B is a derivation. i.e., it satisfies the graded Leibniz rule. The Leibniz rule, the graded Leibniz rule, which is the following. It just says that B of a product, that's a product in Hochschild homology with respect to the product structure defined there, is given by Bx times y, and then we have a sign plus minus, which I'll work out in a second, x times by. And what is the sign here? I guess here we can apply the usual causal rule. So what did we interchange? We flipped the place of x with the operator b. The b operator is a degree 1 operator, so this will introduce the sign minus 1 to the degree x. Okay, that is the relation, and I will just import that as an external fact at this point and not prove this, and I don't recommend trying to prove this. And this is due to the following warning. The warning is that this is not true on the nose on the complex Hochschild homology R relative K. So a priori the easiest reason why this would be true in homology would be that this is just true on the complex. Then this statement would be implied on homology. In fact, unfortunately, it turns out that this is not quite true. It's only true up to chain homotopy, in fact, up to coherent chain homotopy. And there is probably a direct, somewhat combinatorial way of proving that, but we'll just use later, a more systematic way when we describe the con operator topologically and sort of by comparison to the topological approach or by an adaptation of the topological approach, we'll see that this is true here. Nevertheless, this is a very important fact, and this will be crucial to everything that follows. Okay, and now we want to make precise the thing I said earlier, the slogan I gave you, that the con operator is just the de Rham corresponds to the de Rham differential under the HKR isomorphism. And for this we prove the following proposition. And that is, recall that even though this was only an isomorphism under additional assumptions, so now we always had a map omega star R relative K into the Hochschild homology groups R relative K. And the statement is that this map sends the de Rham differential D to the con operator. Operator B, i.e. the following square commutes. Omega star R relative K. And we have the de Rham differential which goes to star plus 1 R relative K. And then here we have this map to the Hochschild homology R relative K. And then here we have a map HH star plus 1 R relative K and this map here, and here we have the B operator. Or another way of saying that would be that this is a module map where both are considered as modules over our algebra A, or graded algebra A. Okay, so how do we prove this? So let's revisit a little bit how this map came along. So the map omega star r relative k into h star r relative k is determined by its effect in degree 0 and 1. Right, so what was the map in degree 0? In degree 0 we just have that the RAM complex is R, and we also saw that the Hochschild homology was R. So here it's just the identity. Let me write this into Hochschild homology 0, R relative K, which is also R. Right, so there it was the identity under this identification, and what happened in degree 1? In degree 1 we just have omega 1 R relative K here, and then we have a map into HH1. And recall in the commutative case, HH1 was just a quotient of R tensor R. We just had R tensor KR, and then a quotient by a certain equivalence relation. The equivalence relation was just given by an alternating sum of 3 maps coming from a triple tensor product. And how was this map defined? The map was just defined by saying we send x dy is mapped to x tensor y. And then the whole map is just defined by extending this. We just use that everything here is generated under products from degree 1 and degree 0. And then this uniquely determines the map. Thus, in order to check the definition, the statement, it is enough to check that the corresponding diagram in degree 0 and 1 commutes. So we have here omega 0 rk, which is R. Then we have the de Rham differential into degree omega 1, which is the Kähler differentials. And here we have our map into Hochschild homology 0 R relative K. And here we have HH1 R relative K. Here we have the B operator. In fact, I'm using a little bit more here, namely that also the de Rham differential is uniquely determined by saying it's a graded derivation and it's determined by its map from 0 to 1. Right, this together with the fact that the map here is determined by its effect in degree 0 and 1 says I can check this just by checking this case. Right? You can very concretely just write down an arbitrary element here, just going to be a product of elements coming from degree 1 and R. And then the fact that both B and D satisfies the graded Leibniz rule will tell you that it's enough to check that this diagram commutes. Okay, but let's verify this diagram. And in fact, I'm going to use the inverse of this map. So here I'm going to use the inverse of this map, which is given by sending x tensor y to x dy, and I'm going to verify that this diagram commutes. But let's check what this diagram does. So this takes an element R here. So we're going to send that to the class of R here. What does our B operator do? Now I guess we have to go into the definition of the B operator. So recall the B operator was the sum over permutations. The corresponding group here is C1. So there is no permutation at all. So it's just a single summand. And the sign was -1 to the n times sigma 0, but n is 0. So all signs are actually going to be +1. And so what we end up finding is that this sends this guy to the class of R tensor 1 minus 1 tensor R. And I guess I messed up signs, so it's supposed, I guess it was 1 tensor r minus r tensor 1. Sorry for that confusion. At this point, I guess you have the chance to go back and check with the definition if I'm right here or I messed it up by a sign. So now let's see, where does this go? This actually goes to, this element, according to this map, has to go to dr. And this guy, actually, r tensor 1, has to go to r times d of 1. But d of 1 is 0, so this goes to r, dr. And that is the same as here. So this commutes, and that finishes the proof. And note, this in particular indicates that this map is an isomorphism, proof that under the HKR isomorphism, the con operator corresponds to the differential D. And we will, in fact, take that as an excuse to often write the operator B or its effect on homology just by a little d. I hope this doesn't, this is common practice in the area very often, and this is just because of this fact. It has the potential of being very confusing because recall on the Hochschild complex we also have an actual homological differential which we denoted partial. So the plan is to stick to the convention that the Hochschild differential is denoted partial and the con operator by d. But in case this could lead to convention, we try to stick to the notation B. Okay, so that was the first example. We saw that under the HKR isomorphism or the HKR map, the con operator corresponds to the RAM differential. And I guess so far we've basically seen, if you've watched the previous video about Hochschild homology, we've basically seen two examples, namely the example of the de Rham complex, the HKR theorem, and the example of the Hochschild homology of the finite field Fp with p elements, p prime relative to the integers. So let's revisit this example in view of our new operator. But unfortunately, this is a little bit of a short story because what was the result? We had the Hochschild homology of Fp relative z. And here we really had to take this derivation replacing by a flat DGA seriously to get this result. This was isomorphic to the divided power algebra on a generator X in degree 2. Right, so additively it's just sitting in every even degree. It's going to be a copy of Fp, but the product structure is according to the divided power structure. And of course, the con operator X trivial for degree reasons. Right, there's no way it can act non-trivial because it just increases degree by 1. So whenever we are in an even degree here, it will go to 0 and vice versa. So it has to act trivially, in fact. And so a question one could ask, does this mean that it is trivial, whatever this might precisely mean, on the Hochschild complex? This could mean that it's, I wanted to write Fp relative to the integers. And my convention will be that if I don't write a basis, then the basis will implicitly always mean the integers. And of course, this could mean several things, being trivial on here. This could mean that it is just 0 as a map on complexes, and this is obviously false. You just need to go into the definition and see that on complexes it's not 0, it's just 0 on homology. But it could mean something like that the map defining it is null homotopic. Or it could even mean that it's quasi-isomorphic as a module to a module where the module action is 0. And this is kind of the question I want to ask here. And the answer is actually no. And how can one detect that, or how can one make sense of this action not being trivial on the complex but still being trivial on homology? And there's one standard trick in the game that we can use here, and this is actually one takes a mod p reduction. So we consider the, and it's actually the derived mod p reduction, which is just Hochschild homology Fp, and I write it mod p to indicate that it's a derived mod p reduction. And how do we define that? This is just defined to be Hochschild homology of Fp. So recall the convention is that this means relative to the integers implicitly. And we're going to take the base change to Fp. And the derived is just put a little L. So if I didn't put the L, it would just a mod p reduction, but that would be somewhat of a boring process here because, I mean, this is already an Fp vector space in every degree. So reducing mod p wouldn't do anything. But of course, we can derived reduce mod p, and that's what we want to do. And of course, a priori, it's clear that this has a module structure over this dg module A, then this guy gets an induced module structure. I just let this A act trivially on this side. And that's what we want to compute now. How the induced con operator on the homology of this guy looks like. And I guess let's just compute what this is as a algebra first of all. So again, Fp is an algebra, though this will inherit an algebra structure. And so in particular, the homology will be a graded commutative algebra. Let's compute that first. So how do we do that? I guess this is equivalent. The way to do that is our usual way. We just resolve Fp over the integers. So this is just going to be Fp, the complex. And we tensor with the algebra, which is, I mean, maybe let me denote it like this. The exterior algebra over the integers on an element epsilon, where epsilon is degree 1. And where I define a differential partial epsilon is equal to p. Right, that's quasi-isomorphic to Fp, same way that we did before. And then we can just take this tensor product, because this guy is level-wise flat over the integers. And what is this tensor product? I guess now the point is that this is in fact an Fp algebra, as we saw earlier. So we can actually, instead of tensoring over Z of this guy, we can tensor over Fp with a mod p reduction. So this is the same as Fp. And then we tensor over Fp with the mod p reduction of this guy. But this is now just the exterior algebra over Fp on epsilon, and there is no differential here. No differential. Since, I mean, there is a priori differential, partial, but partial of epsilon is actually p, and this is 0, because we've reduced mod p. So this is actually an equivalence of chain complexes. Everything is flat here. So the result is that the Hochschild homology, and I guess I should write the homology of this mod p reduction, mod p, that is as a graded algebra, just the homology of that guy. Everything is flat, so we're going to end up finding that this is the Hochschild homology of Fp tensored over Fp with an exterior algebra, lambda Fp epsilon. And remember, this is a divided power algebra, so we're going to have that this is Fp divided power on a generator x in degree 2, x in degree 2, and epsilon in degree 1. So tensored over Fp with exterior algebra on a generator in degree 1. Okay, and now the cool thing is, by doing this reduction, we have now, so if you expand this additively, you have an Fp in every degree. So there the con operator is not necessarily trivial for degree reasons. And in fact, it turns out that we have the following proposition. Namely that we have, and now maybe let me write this as B again, and not yet stick to my convention that I want to write the con operator as D always. So we have that B, I mean, there are the divided powers of x. So the nth divided power of x is written x upper brackets n. I guess it was also previously written as gamma n of x. So the claim is that these all vanish for all n. And secondly, it's a con operator, by the way, the convention is that for n equals 0, this is just 1, the n's divided power. So of course also the Conn operator vanishes on 1, but this is already clear from the Leibniz rule. And then actually there's b of epsilon, and the claim is that this is given by x. And there's a little fine print, namely that now in the proof we'll exactly see in a second what this is, and one might have to change the previously defined x by a unit. So implicitly this means there could be a unit in fp cross coming in here, but then we'll just redefine x so that this holds on the nose. In other ways, this gives you a way of gauging x by just saying it has to be b of that epsilon. Okay, so, and I guess in general then from this and the Leibniz rule you can deduce that, I mean this implies and could be taken as part of the result that, I mean the additive basis of my homology here is given by epsilon x to the n. And now I guess we can use the Leibniz rule to figure out what that is. So b vanishes on this guy, so we just have to evaluate it on epsilon. So we're going to get that it's x times x to the n. And of course, this is given by x to the n plus 1. I mean, this is implicitly, remember, this, we think of this element as x to the n over n factorial. So this is basically x to the n plus 1 over n factorial, which is the same as n plus 1 times x to the n plus 1. Okay, and now after wiping the board, I'll give the proof of that statement. Okay, so we want to prove that our Conn operator on this mod p reduction has the following behavior. And first of all, we know that the map, the reduction map from Hochschild homology fp down to its mod p reduction, mod p is compatible with b by definition of how we defined the b operator on this mod p reduction of Hochschild homology. Thus it follows, let's see how does this map look like on homology. So this was concentrated in even degrees generated by these divided powers, and this was concentrated in even degrees by the divided powers, and then we had epsilon times those guys in odd degrees. But since this map is compatible and we know b sends this guy to 0 here, it immediately follows just from this compatibility that b has to be 0 on those elements here too. Okay, so compatible with b, thus we get the first claim that b of those elements is 0 in the homology of this mod p reduction as well. Mod p. So therefore it really only remains to compute this guy. And for this, let's try to remember how we computed Hochschild homology of fp. So the way we computed, the way Hochschild homology of fp, or the homology groups, being the divided power algebra, is computed is by replacing fp by, fp is not flat as an algebra over the integer, so we had to replace it by the algebra z, exterior algebra over z epsilon, with the differential partial epsilon equals p. Right, and then you can either carry out with this replaced algebra, you either carry out the formula that the Hochschild homology of a ring is given by the ring tensored over a ring tensor ring op with a ring, or you just run the bar complex. That's the very definition of Hochschild homology. Right, so what is the bar complex, or what's the cyclic bar complex going to look like? So we're going to put lambda z epsilon here, and then we have the tensor product lambda z epsilon, tensor lambda z epsilon. Then we have our two maps here, our two multiplication maps, and then we had our three maps here. And maybe I don't write it simplicity, but I immediately write it as a differential, and then I have like 3 copies and so on. Right, now let's work out where the element x sits. So this is now a double complex, right? If you write this as a double complex, let me maybe do that. So here, the first column in this double complex is the exterior algebra lambda z epsilon. And the second column is the tensor product of the exterior algebra with itself. So that's an exterior algebra on two generators, epsilon tensor 1, 1 tensor epsilon. If you work out what the differential is, I mean, this will not matter for what we do. The differential is given by p comma p here and minus p comma p here. And here you have the class of epsilon tensor epsilon and so on. So the crucial point to observe here that the class x that we termed x earlier is given by 1 tensor epsilon minus epsilon tensor x. And that's a cycle in this complex. So this cycle is detected here in this double complex, right? And now the point is that we can work out what the con operator is. So there's an element epsilon here, right? This element epsilon is not a cycle in this complex over the integers because it supports the differential. The differential here is p, but still it exists as an object in this double complex, and we have that if we evaluate the b operator on that epsilon, then actually we get by the formula for the b operator, in this case again we have a single copy of epsilon, so the crucial group here, the permutation group is C1 here, which is just a single permutation, and again we're going to get that this is just given by 1 tensor epsilon minus epsilon tensor 1. Actually, in fact, you have to be a little bit careful with signs, but this is the way signs work out by the formula we had earlier. The Hochschild sign rule doesn't force us to interchange anything. Okay, so on the complex level, we already see the epsilon here. It's just not a cycle. But still, we have that the con operator takes epsilon to the class of x. And now, after mod p reduction, we replace all copies of z in this diagram, all z's, by fp. Then epsilon becomes a cycle. The class epsilon is a cycle, which is exactly the epsilon which we detect on the homology groups, and we get that b epsilon is the class of x on homology. Maybe I should write classes. And that finishes the proof of the computation of the con operator on the Hochschild homology Fp, or at least some part of it. So we see that it's non-trivial on the homology, on the chain complex, while it is trivial on the naive homology. And that can be detected by the mod p reduction. Okay, so that is everything I wanted to say about the con operator for today. Thanks for watching, and stay tuned for the next video, which will tell you why we talked about the con operator, and that is cyclic homology.